This is Math 105, Section 3.5. We're just going to look at Section 3.4 in class briefly. We're going to look at maybe one or two concepts from that section. So I won't do a video lecture on Section 3.4. Okay, so we talk about complex numbers in this section. And remember we talked about the discriminant of a quadratic equation. That was where your, b squared minus 4ac is what's in the square root when you do the quadratic formula, right? So when that's negative, remember we said the equation has no real solution, that you can't take the square root of a negative. So for example, x squared plus 4 equals 0 gives us x squared equals minus 4, and that gives us x equals plus or minus square root of minus 4. But remember, we can't take the square root of a negative, at least in real numbers, okay? So we said this has no real solution, right? In other words, this thing does not have, if this were y equals x squared plus 4, that would not have crossed the x-axis, because when you set y equal to 0, you get no solution, okay? Because when you square any number, you can only get a positive. So we say negative numbers don't have real square roots. So we don't have a solution to this in real numbers. But what we can do, we can expand our number system, and we call this expanded number system the complex number system. So this is an expanded number system, and it also includes negative square roots, okay? So first we define this new number as little I equals square root of minus 1, okay? So that's our first thing that we define, okay? And then when you square it, remember that cancels the square root out, so I squared is just minus 1, okay? So we start with that. That's called our imaginary unit, okay? And then we can say our complex numbers now follow this form, okay? A plus bi, and a and b are real numbers, okay? But that I is the square root of minus 1. Okay, so when we ever have a negative square root, we can turn it into something involving I. Okay, for example, I'll do a quick one here. Square root of minus 4, which we saw on the previous page, is the square root of 4 times a minus 1, right? Which is square root of 4 times the square root of minus 1, just using our rules of radicals, right? And this would just be 2 times I. Okay, so we can call that 2i instead of square root of minus 4. So when we use that imaginary unit, now we can talk about negative square roots, okay? In fact, any square root we can write using I. So like square root of minus 17, for example, which does, is a prime number, we can write as the square root of 17 times I. Now remember that I would be outside the square root because it is a square root, right? It's a square root of minus 1. So that's kind of, I didn't show the work there, but shortcut, you can take square root of minus 17 is square root of 17 times I. Okay, so what we can just do is take the negative out of the square root and put an I on the outside, and it's the same form. It's equivalent. Okay, so a complex number is an expression of this form, a plus bi. Okay, where a and b are real numbers. I squared is minus 1, or I is a square root of minus 1. Okay, the real part is a. Okay, so that's the first real number, that's the a, and the imaginary part is b. So the imaginary part is not a, it's the part that is not I, it's the part that's times I. Okay, and then we say two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. Okay, so we should also note here that both the real and imaginary parts of a complex number are real numbers. Okay, so for example, if we have 3 minus 4i, okay, as our complex number, the real part, a, is 3, okay, and the imaginary part is not I, but it's the part that's times the I, okay, so the imaginary part is minus 4, okay, so we have a negative because it's minus 4i. Okay, so some examples here. For 3 plus 4i, the real part is 3, and the imaginary part is 4. Okay. Here for 1/2 minus 2/3 I, the real part is 1/2. The imaginary part is minus 2/3. For 6i, the real part is 0. Notice we don't have a something plus, so the real part is 0, and the imaginary part is 6. And here, this is also a complex number, it just doesn't have the I part. So here our real part is minus 7, and our imaginary part is 0. So it's worth noting here that complex numbers include all the real numbers too, like minus 7 or even 0. 0 is a complex number because we could write it like this. 0 would be the real, would be 0, and the imaginary part would be 0. Okay. In this case, a and b are both 0. Okay, so these are also considered complex numbers, even though they don't have an I in them. So what complex numbers does is it expands our number system of real numbers to include this I part as well, that square root of minus 1. Okay, so the key to remembering when we do adding, subtracting, multiplying, or dividing with complex numbers, we do those just as we would any number of the form a plus b times square root of c. Okay, so the only difference is that we need to keep in mind is that I squared is minus 1. So when you get an I squared, you change it to minus 1. Okay, so we can do a plus bi times c plus di by multiplying a times c. Okay, and then AD plus BC times I, and then BDI squared, where we're using FOIL, but I'll show you with examples. Okay, and then we're combining the two I parts together, right? And then the I squared, remember, just becomes minus 1. Okay, so we have BDI squared becomes BD times minus 1. Okay, so that gives us AC minus BD because we're combining these like terms here, here, and here. Okay, and then we add the parts that have I on them, so just AD plus BC. Okay, but think FOIL when we're doing this. We multiply. This is like a binomial. It's like a plus bx. This is like c plus dx. Okay, so we're multiplying a binomial times a binomial. So whenever you're multiplying complex numbers, you can use FOIL. Okay, let's do some arithmetic operations on complex numbers. So when you do addition, here we have two different complex numbers with a and b as our real and imaginary part for the first one, and c and d is our real and imaginary part for the second one. Basically, we're just adding, think of these like a variable, sort of like this is like b times x and this is d times x. And what we're really doing is adding like terms in a sense, if we treat I like a variable. So we're going to add the real parts, the a plus c, and then we're going to add the imaginary parts, b plus d, and multiply it times I. Okay, because this is bi and this is di, so we add the b plus d times I. So that's kind of how what we're doing is treating I like an x, like a variable. Okay, even though we know it's square root of minus 1. Okay, so to add complex numbers, add the real parts and add the imaginary parts. Okay, subtraction, just subtract the real parts and subtract the imaginary parts. So a minus c, okay, and then bi minus di or b minus d times I. Okay, make sure when you're subtracting, there's two parts to this part you're subtracting, so you got to change the sign of the c and of the di. Okay, for subtraction. So be careful with that. Okay, multiplication. This is like a binomial times a binomial, so we're going to use FOIL. Okay, so basically you can use FOIL here too. So if we use FOIL on the multiplication, okay, you would do the first, which would be a times c. Okay. The outside, which would be a times di, so there's the ADI, okay, and then the inside, which is b times c times I, okay, and then the last is b times di squared. Okay, so let me write that out just so we see that. So FOIL would give us AC plus ADI, a times d times I, okay, plus b times c times I, so BCI. And then that last one would be plus BD times I squared. But remember, I squared is just minus 1, so we can actually cross out the I squared and just write minus 1 there as a multiplication. Okay, so that's how we get that minus BD there. Okay, because it's BD times I squared, and that's just minus BD. And then here's the AD and the BCI. Okay, and they're just grouped there. Okay, so we can use FOIL when we multiply complex numbers. Okay, let's look at an example. Let's say we're looking at 3 plus 5i plus 4 minus 2i. We're going to add the real parts, so 3 plus 4. Okay. And then we're going to add the imaginary parts. So 5i minus 2i would be minus 3i, or 5 minus 2 times I. Okay. Or sorry, plus 3i. 5i minus 2i would be plus 3i. Okay. So we can think of these as like terms. We're combining these like terms. 5i minus 2i is 3i. Okay, so there's our answer for addition. Okay, for subtracting complex numbers, 3 plus 5i minus 4 minus 2i. Notice we have parentheses here because we're subtracting that whole complex number. So 3 minus 4, and then 5i minus a minus 2i. So make sure you apply that negative to both of these. Change the sign of this to minus 4 and this to plus 2. So really this is going to be 5 plus 2 times I, which is 7i. So this would give us 3 minus 4 is minus 1. 5 minus minus 2 would be 7 times I. Okay, so it would be minus 1 plus 7i would be our answer there. Okay, for multiplying, FOIL. Okay, so we can do FOIL or we do the rule that they said before. So 3 times 4 is 12. Okay, but we also have 5i times a minus 2i, which is minus 10 times I squared, right, which is plus 10. So 12 plus 10 would give us 22. So we're not doing FOIL there, but we can do FOIL as well, and it gets the same answer. Okay, the outside is minus 10i. The inside is plus 20i. So that gives us a minus 6i for the outside and a plus 20i for the inside. So minus 6i plus 20i will give us a 14i. Okay, so there's the minus 6 plus 20. Okay, and then notice they're doing 5 times minus 2 and they don't have the I there because what they're doing is just changing the I squared to a minus 1 there. Okay, but doing FOIL will give us the same answer there. So here's how we get our answer using FOIL. Our first would be 3 times 4. Okay, our outside would be 3 times a minus 2i. Our inside would be 5i times 4, and our last would be 5i times a minus 2i. Okay, and that gives us 12. Okay, minus 6i, 3 times minus 2i, plus 20i. Okay, and then minus 10i squared. And I'm not going to show the next step of simplifying, but you know, minus 6i plus 20i gives us 14i, right? Okay. And then 12, now remember that I squared can just be changed to a minus 1, so it would be plus 10. So 12 plus 10 would give us a 22. Okay. And then finally our last one, and we'll look at different powers of I in class, but I to the 23rd, that means we're multiplying I 23 times. But remember that anytime we take an even power of I, it's just minus 1. Okay, because this is just, you know, 2i squared to the 11th is I to 22. So this is just minus 1 to the 11th. Okay, so we can say this is I to the 22 plus 1, right? Because we're taking the even power out. And then that's I to the 22 times I to the 1. So this is kind of, they didn't show that intermediate step there, but this, let me show the intermediate step there. So this is I to the 22 times I to the 1. Those are i's there. Okay. So that's our intermediate step, and then we can say, well, I to the 22 is just I squared to the 11th, right? Because we multiply, right? So we're kind of doing that part of exponents backwards, and I squared is just minus 1, so that's minus 1 to the 11th, which is minus 1, because we're taking negative 1 to the odd power, times I, so it's just minus I. Okay, and I'll show you a trick in class how we can do it a different way for higher powers of I. Okay, okay, so for division of complex numbers, we need to rationalize the denominator. So we need to be rationalizing the denominator just like a radical expression we would, okay? So what we do is when we have a number, let's say z as a complex number, that's a plus bi, we want to multiply it times its complex conjugate. Remember we talked about conjugates with the radicals. Now we're going to talk about complex conjugate. Okay, so if z is a plus bi, then its complex conjugate is a minus bi. So we're going to change the sign of just the imaginary part. Just the plus bi becomes a minus bi, and vice versa. Okay, so so we put a bar over the z to show it's a complex conjugate. Okay, so and we multiply a number z, complex number z, times its complex conjugate. We have a plus bi times a minus bi, and that just gives us a squared plus b squared. And the reason for that is this. When you FOIL this, a plus bi times a minus bi, you get, multiplying your first, you get a squared. The outside is a times minus bi, so that's minus abi. The inside is a times plus bi, so that's plus abi. And then our last term is minus b squared times I squared. Okay. Now these cancel, these inside-outside terms, right? And then the last term, minus b squared, because we have a plus bi times a minus bi times I squared. This, remember the I squared is just a minus 1, so that would give us a plus b squared. So that's how we get that a squared plus b squared. Okay. So we can say now, hey, we can factor the sum of squares, but we have to use I to do it. Okay, so you can only, now remember we said we could factor the difference of squares. You can actually factor the sum of squares if you use I. Okay, because this is what it would be. A plus bi times a minus bi is a squared plus b squared. Okay, but the reason we're doing this is because we might have an I in our denominator, and we want to get rid of it. So we multiply it times its complex conjugate on the top and bottom to get rid of that. Okay, so here's the formal definition. Let's say we have this, we're dividing these two complex numbers. In this case, we have c plus di in the denominator. Okay, we multiply the numerator and the denominator by the complex conjugate of the denominator. Okay, so that's worth noting there. Multiply the numerator and the denominator by the complex conjugate of the denominator. Okay, so in this case, we're going to take a plus bi over c plus di and multiply it times c minus di over c minus di, the complex conjugate of the denominator. Okay, and we don't have to FOIL this because we already know this, but if you did, you're just going to get c squared plus d squared in the denominator. Okay, and then you have to FOIL the top, so you're going to get some complex number on the top that involves I. But the key is that your I disappears in the denominator. Remember, I is a square root of -1, so we want to get rid of the square root in the denominator. So it is rationalized in the denominator, when we do this. Okay. So we take the complex conjugate of the denominator, multiply the top and the bottom to get rid of that I in the denominator. Okay, so let's look at a couple of examples. First we'll look at 3 plus 5i over 1 minus 2i, and then we'll look at 7 plus 3i over 4i. Okay, and we're dividing complex numbers. Okay, so the first one, 3 plus 5i over 1 minus 2i, we're going to multiply this fraction times the complex conjugate of this, top and bottom. So the complex conjugate of this is 1 plus 2i. We just change the sign of the imaginary part. Okay, keep this the same. Okay, and multiply the top and the bottom times that complex conjugate. So complex conjugate of 1 minus 2i is, we put that bar over it to represent complex conjugate, which is just 1 plus 2i. Okay, when we FOIL this, on the bottom we get 5, and on the top we get minus 7 plus 11i. And just to kind of show the intermediate step there, so if I FOIL on the top, I get 3 times 1, and then I get 3 times 2i for the outside, 1 times 5i for the inside, and then 5i times 2i, or 10i squared for the last. That's a plus there. Okay, so the I terms would be 6i plus 5i, which gives me 11i. And then this is no longer an I term because this is just 10 times minus 1, so this is minus 10 plus 3 gives us a minus 7. Okay. And then remember, this is a squared plus b squared from what we did before, so that's just 1 squared plus 2 squared, or if you FOIL it, you'll get the same thing, which is 5. Okay. Okay. The important thing is, once we do this, write out the real part and the imaginary part of your complex number separately. So this would be minus 7 fifths plus 11 fifths I. Okay. So don't use this form as your answer. Use this form, and that's a plus bi form. Okay. So we'll write that down as a plus bi form. Okay, that's important that we do that so we can see where the parts are. The a is minus 7 fifths, okay, and the b is 11 fifths times I. So b is our 11 fifths. Okay, so we got our answer here, but we have to put it in this form. Okay, our next example was 7 plus 3i over 4i. So all we have to do is change the sign of the imaginary part. So this 4i becomes minus 4i, and we multiply the times the top and the bottom. Okay. Okay, and just showing the intermediate step there. Distributing the minus 4i and the 7 plus 3i, we get 7 times the minus 4i. Okay. Minus 3i times 4i, because we have minus here. So, okay, so this gives us minus 28i. And this is minus 3 times minus 4 is 12 times I squared. So minus 12i squared is a plus 12, because remember, I squared is minus 1. And then the denominator is minus 16i squared, which is just plus 16, because I squared is minus 1. Okay, so that's the simplified version of that. Okay, is a single fraction, but remember, we have to break out the real part and break out the imaginary part. So 12 sixteenths is 3/4, and then minus 28 sixteenths is minus 7/4. Simplify your fractions too. So this would be our simplified version of that. Notice with the a and the b separate. So a plus bi form for those. Okay, just want to note something about negative square roots. Remember this, square root of a times b is square root of a times square root of b, right? We know that by rules of exponents, okay? But that's only true when a and b are positive, okay? It's not true when both are negative, so we have to be careful of that. So here's an example where we have square root of 2 times square root of 3, and we would write it as we could, let's start with this. Square root of minus 2 times minus 3, right? Okay, so this is kind of where our mistake is. That we have this is actually square root of 6, right? Minus 2 times minus 3, right? And if we break them out as two negatives and then break them out separately, notice what happens, right? We get, so this is square root of 6 here. Let me write that as square root of 6 down there. Okay. Okay. I know it steps underneath, but if we break them out as separate as negatives and then separate them, we're going to get square root of 2 times I and square root of 3 times I, so we get square root of 6 times I squared, which gives us a minus square root of 6. Okay, so this is not true. Okay, so we cannot. Here's where the problem is, right here. We cannot break those out separately because we have two negatives. So we have to be careful with that. We can't break these out separately when we have two negatives. Okay, so the the key here is when multiplying radicals of negative numbers, express them first in the form square root of r times I, okay, to avoid possible errors of this type. Okay, in other words, don't break out the negative separately. Okay, if you have two negatives, you can't separate them. Okay, so that's the only exception to that. Okay, now we're going to look at complex solutions of quadratic equations. This is, we in the past when we've got negative square roots, we just ignored it, right, and say there's no solution. Okay, but now we're doing our quadratic formula: x equals minus b plus or minus square root of b squared minus 4ac over 2a. Right? Remember we said if that discriminant is less than 0, the equation has no real solution, right? But in the complex number system, we will always have solutions, okay? Because we can take square roots of negative numbers, okay? Because negative numbers have square roots in this expanded setting. So now we can actually get two solutions that are complex. Okay, so let's look at a couple examples. X squared plus 9 equals 0. That would be finding the x-intercepts of y equals x squared plus 9, right? Okay. That means x squared equals minus 9, right? Which means x equals plus or minus square root of minus 9. But remember, that's not, we can't take a negative square root, right? But now we can with using I, okay? So that would be plus or minus 3i, okay? So the solutions are 3i and minus 3i for this, using the real solutions, okay? Now, we can also factor it. So we could say this: x squared plus 9 equals x minus 3i times x plus 3i. And we'll get to this in another section, but what you're doing is you're taking those, remember these are our zeros, right? This is where this thing's equal to 0. So we take x minus 1, 0, which is plus 3i, and then x minus the other 0, which is x minus a minus 3i, we'll get our factors. Remember using our factor theorem? Okay. So we can actually factor this using complex, numbers. Okay. All right, and the next one, x squared plus 4x plus 5, we'll look on the next slide. Okay, so using our quadratic formula, we have x equals minus b plus or minus the square root of b squared minus 4ac. Okay. Remember, a was 1 and c was 5 and b was 4. Okay. Over 2a. Okay, so minus 4, this is going to be 16 minus 20, which is minus 4 square root. So minus 4 plus or minus square root of minus 4 over 2. Or we can write this as 2i. So minus 4 plus or minus 2i over 2. Okay. And then if we factor out a 2 here, it's a little bit easier. So if we factor out the 2, these cancel, right? So we just get minus 2 plus or minus I. Okay. Now notice about this one and the last one, the solutions that are complex to these quadratic equations always come in pairs, and the pairs are complex conjugates of each other. So if we have minus 2 plus I as a solution, we also have minus 2 minus I. Okay. In the last one we had x equals 3i and minus 3i. So they always come in pairs, and they're complex conjugates of each other, and the reason is because we have a plus or minus in front of that square root. And that's the negative that gives us the I. Okay, so just to formally state that, if a quadratic equation with real coefficients has complex solutions, which we just looked at in those last two, then these solutions are complex conjugates of each other. So we can say if a plus bi is a solution, then a minus bi is also a solution. So if we're given one, we can find another one, okay, just by taking the complex conjugate. Okay, we'll look at some more detailed examples in class, but I want to give you a general idea of how we deal with complex numbers and why.